Every time you flip a light switch, you're trusting that this huge, incredibly complex system is working perfectly behind the scenes. But what happens when something goes wrong? Today, we're going to pull back the curtain on the amazing, unseen tech that acts as the guardian of our electrical world, making sure it all stays safe and reliable. And believe me, that's not some hypothetical sci-fi question. It is the absolute core challenge for engineers managing high-voltage power grids. When you try to interrupt that much electricity, it doesn't just stop. Oh no, it fights back with an unbelievable amount of force. Okay, let's dive into this. Here's our game plan. First, we'll look at the high-voltage challenge itself. Then, we'll meet the amazing supergas that's the key to the solution. After that, we'll see exactly how it quenches that arc, look at a few different designs, and finally, wrap up with why these things are so critical, why they really are the guardians of the grid.
To really get why the solution is so brilliant, we first have to wrap our heads around the sheer scale of the problem. We're not just talking about flipping a switch, we are talking about taming a force of nature inside a metal box.
So imagine you could pull two giant live wires apart. The electricity desperately wants to keep flowing, so it literally leaps across the air between them, and it creates this brilliant, intensely hot channel of plasma. Now, this isn't just a little spark, it's a contained man-made lightning strike that can melt steel and cause catastrophic failure if you don't extinguish it in milliseconds.
And just look at the kind of power we're trying to control here. 800 kilovolts, and that's not even the ceiling. That is a mind-boggling amount of electrical pressure. To give you some perspective, your outlet at home is probably 120, maybe 240 volts. This is thousands of times more powerful, and these breakers have to stop it dead in its tracks. So, how in the world do you fight something as powerful as electricity itself? Well, you use a substance that's basically designed to be its kryptonite. You use a unique, powerful gas that acts like the ultimate electrical firefighter. And here it is, meet sulfur hexafluoride, or SF6 for short. This stuff is the hero of our story. It's a synthetic gas with two real superpowers. First, it has incredible dielectric strength. Just think of it as being electrically bulletproof. It's a fantastic insulator. But its real magic trick? That's its electronegativity. Now, what's really interesting about this slide is that electronegativity property. So what does that even mean? Well, it means the SF6 molecules are incredibly greedy for any free electrons they can find. That electrical arc, it's basically just a river of free-flowing electrons. So when the SF6 gas hits that arc, it acts like a super absorbent sponge, just soaking up all those electrons and completely smothering the arc at its very source.
So we've got the breaker and we've got the supergas. Let's move on and see how they work together in this beautiful high-speed electromechanical dance to get the job done literally in a flash.
It all happens ridiculously fast. First, some kind of fault is detected. A signal goes out. Then, as the mechanical contacts inside the breaker start to pull apart, bam, that arc is born, but instantly, a piston fires a high-pressure puff of SF6 gas right into the arc's path. The gas grabs the electrons, the arc just vanishes, and the gas's insulating property makes sure it can't reignite. The whole thing is over in a tiny fraction of a second.
So the crucial point is this. It's a really good way to think about it. An SF6 circuit breaker is basically a highly specialized, incredibly fast, and super powerful fire extinguisher, but one that's designed only for electrical fires. It doesn't just stop the flow, it puts out the fire itself.
Now, this core technology is absolutely brilliant, but it's not a one-size-fits-all solution. Nope. Engineers have cleverly adapted the basic design into all sorts of different forms to meet the specific needs of the power grid.
And one of the most fundamental differences you'll see is this: live tank versus dead tank. It sounds a little dramatic, right? But in a live tank design, the interrupting part itself is sitting at the same dangerous high voltage as the power line. In a dead tank design, that same part is tucked safely inside a big metal tank that's connected to the ground, making it dead or safe to touch. They both have their pros and cons, and you'll see them used in different places all over the world.
And just to be clear, this isn't some niche, experimental stuff. This is the gold standard, and it's built by the absolute heavyweights of electrical engineering. We're talking about companies like ABB, Siemens, General Electric. They're all building the devices that form the backbone of our entire global power system. Okay, so let's zoom out a bit. We've dug into the problem, and we've seen the really elegant solution.
But where are these guardians actually standing watch? And what does it all mean for us, really?
Honestly, they are everywhere. You'll find them in those massive substations you see on the side of the highway, in super compact switchgear hidden away in big cities. At every kind of power plant, they even protect renewable energy sources like wind and solar farms. They're vital for railways, huge factories, big office buildings, basically anywhere large amounts of power need to be controlled. SF6 breakers are on the job.
And this brilliantly illustrates just how seriously their reliability is taken. It has to be perfect, right? So they go through these 3 intense levels of testing. Type tests to prove the initial design is sound. Routine tests on, get this, every single unit that leaves the factory. And finally, site tests once it's installed to make sure it's working perfectly in the real world.
So the next time you're in a thunderstorm and the lights flicker for just a second and then come right back on, you can probably thank one of these unseen guardians. That little flicker was likely a fault out on the line, and an SF6 breaker detected it, isolated it, and restored safe power to you, all in less time than it took you to even notice. Their role today is more important than ever. But as our grid gets smarter and more complex with renewables and all sorts of new controls, it brings up a really interesting question. You see, while SF6 is an incredible gas for this job, it's also a potent greenhouse gas. The industry knows this and is working hard on alternatives. So it makes you wonder, right? What will the next generation of grid guardians look like? What new tech will keep our world energized and safe? Well, that's the next chapter in this incredible story.